Hi all. Today's topic is section P9. We're looking at linear inequalities and absolute value inequalities. Now the beginning of this section goes back and it talks about interval notation versus our set builder notation versus number lines. So we'll look at that and then we'll get into solving inequalities and the absolute value inequalities. So you see that the learning objectives, we will make sure you know how to use interval notation. We'll find intersections and unions of intervals. Then we'll work on solving linear inequalities and then make those more fun by making them compound inequalities. And then a related topic with compound inequalities is the absolute value inequalities. Compound inequalities is where our variable is in the middle and we say it can be greater than one number but less than another. And that really carries over nicely to the absolute value inequalities. So first of all, if we're solving an inequality, it's the process of finding the set of numbers. So instead of what we're used to with equations where we say x is equal to some specific number, with inequalities it's going to be equal to a huge set of numbers, probably an infinite set of numbers. So you can't simply just say it's any one specific value. So we find a set of numbers or an interval of numbers that make the inequality a true statement. These numbers are called solutions of the inequality, and we say that they all satisfy the inequality. The set of solutions is called the solution set. Okay, now, because it is a solution set, you can represent it with set notation, or you could represent it with interval notation. My personal preference is the interval notation myself. If I say the open interval from A to B, it represents the real numbers between but not including A and B. So if I wanted to say X is all numbers between A and B, I would represent it as parentheses A up to B, parentheses, that shows it's all numbers in between, but not including A and B. In the set builder notation, you could say it's the set of all X such that A is less than X, which is less than B. And then of course you would close out your set builder notation. Remember, closed interval just means that the endpoints are included. So if I wanted to represent that X is all numbers between A and B, and it could also equal A and B, I would just put brackets around A and B. And in my set builder notation, the only difference is my strictly less than signs become less than or equal to. So A is less than or equal to X, which is less than or equal to B. So anytime you have an equal sign in your less than or equal to's, you're going to have brackets around your endpoints. If you don't have an equal signs in your inequality, like above, you're always going to have parentheses around your endpoints. Now, what if I wanted to represent X is all values greater than some number A? Well, okay, that's pretty easy. If it's greater than A, then A is not included. And then it's any number greater than A, well, that means it could go all the way up to the largest possible number, namely infinity. Of course, you can't reach infinity, so it always has a parentheses, just like we have a parenthesis around the A, since you can't equal A. Now, again, I prefer the interval notation. The set builder notation here, it would just be the set of all X such that X is strictly greater than A. Now, what if I'm trying to represent the set of real numbers that are less than or equal to B? All right, well, you can see I already have it here. It's the X's would be equal to the interval of all numbers starting at negative infinity, going up to B, and the bracket means it could also include B, but this shows that B is the largest possible number in that set. Well, the set builder notation for that would be X such that X is less than or equal to B. Now, please do keep in mind parentheses will indicate that the endpoints are not included. Brackets indicate that the endpoints are included. Because that's the scenario, please, 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 please remember, you never ever put brackets around infinity or negative infinity. You can't reach the infinite. You can't reach the negative infinite. So we always use parentheses around them. Now, with that in mind, if I look at a problem where I'm trying to represent the set of numbers between 1 and 3.5, including 1 and including 3.5, a number line is really easy. You could just carry out the exact same notation and say, well, you're including 1. So you can put a bracket on 1. You include 3.5, put a bracket on 3.5, and it's all numbers in between. So you shade what's in between, or you'll see what I did in my homework solutions. I'll kind of draw an arc between 1 and 3.5. Now, another thing I will do, instead of the brackets, I'll put points on the line to show that those numbers are included. If I wanted to exclude the numbers out by hand, I'll usually do circles on the graph to show that they're excluded, because that carries over more to graphing better than these brackets and parentheses. The reason I kept the brackets and parentheses in the PowerPoint demonstration for you is because that's how my math lab will have you work the problems whenever you go online and try to fill these out on a number line. It'll have you do either the bracket or the parenthesis. Now, please do notice, well, it's all numbers between 1 and 3.5. The set builder notation is easy. You just always say, we'll put the lowest value on the left-hand side, and then can it be included? Sure. So it's less than or equal to X, which has to be in this region, and then that's less than or equal to the largest possible number, 3.5. That would be our set builder notation. Now, if I'm trying to do the set builder notation between negative infinity and 1, I would just say, well, all right, then X is less than negative 1. Do I need to say X is greater than negative infinity? No, it goes without saying. Every single number in existence is greater than negative infinity, so you don't have to say it. So all you have to say is that X is less than negative 1 in your set builder notation. Now, similarly on your number line, you don't plot out negative infinity on your number line. It's not a number, it's not a real number. So all you have to do is, and what I would do is just plot out the number negative 1. I'd put a circle around it. A parenthesis is fine though. And then you shade forever to the left, because this is going to go forever to the left, that negative 1. It can never go to the right. Now, in general, whenever we're trying to find intersections and unions of two intervals, it's probably helpful to graph the intervals on a number line. It's not required, but helpful. To find the intersection, we're going to take a portion of the number line that the two graphs have in common. So in order to be in an intersection of two groups, it must be in the first group and it must be in the second group. Now, if we're finding the union as opposed to that, we take a portion of the number line representing the total collection of numbers from the two graphs, meaning if it's in either group, it's in the union of the two groups. So it's in the first group or it's in the second group, then it's in the union of the groups. Union is always going to be greater than or equal to the size of the intersection. The intersection is at most the same size as the union. Now, if I'm asking you to determine the graphs, or sorry, use the graphs to find the set of, I want to find the intersection between the set of numbers between 1 and 3, and that's 1 and 3 inclusive, and then the set of numbers between 2 and 6, where 2 and 6 are not included. All right, well, if I'm trying to find the intersection there, I can say, well, my first group is just all numbers between 1 and 3, including 1 and 3. The second group, it's going to start at 2, but not include 2, and then go all the way up to 6. So I can say, well, the intersection has to be numbers that are in both this group and this group. And so you can quickly and easily say, well, what about the numbers between 1 and 2? No, because it's not in the second group. Well, what about the numbers starting at 2? 2 itself, even though it's in the first group, it can't be included because it's not in the second group. And then you'd say, okay, I'll have to start at 2, not including 2, and then I can go up to 3. Can I include 3? Sure. 3 is a number in the second group, 3 is a number in the first group. So this is going to be the solution set from 2, not including 2, since it's not a point in the second group, up to 3, and bracket at 3, since 3 is the ending point that's included in the first set of numbers, and it's also included in the second set. So we'd say our intersection there is the set of numbers between 2 and 3, including 3, excluding 2. Now, if we talk about a linear inequality, typically that's just when we have something like ax plus b is either less than 0, less than or equal to 0, greater than 0, or greater than or equal to 0. Now, the only thing you need to remember here is that you solve an inequality the exact same way you solve an equation. The only exception to that, and I have it right here in bold print, when we multiply or divide both sides of an inequality by a negative number, the direction of the inequality symbol is reversed. So if you divide by a negative a on each side, then if it was greater than to begin with, it's going to change to less than. If it were less than or equal to begin with, it's going to change to greater than or equal to. Let's see that in action here. If I ask you to solve the solutions or find the solution set to the number and a number line solution to 2 minus 3x is less than or equal to 5. All right. Just like in an equation, I say I need to get x by itself. What's the first and best step to do that? Well, I'll get rid of that 2. It's an understood positive 2, so I subtract 2 on each side. I get negative 3x is less than or equal to 3. Notice you don't flip the inequality just because you subtracted 2 on each side. The only time you flip the inequality is when you multiply or divide by a negative, but now I'm doing that. I can say, well, in this next step, I need to divide by negative 3. When I divide by that negative 3, that less than or equal to has to flip to be greater than or equal to. And then I'll get positive x is greater than or equal to negative 1. So now that would be my set builder notation solution, the set of numbers x such that x is greater than or equal to negative 1. In interval notation, we would just say, well, the x value that starts being a solution is negative 1, and it can include negative 1. So I'd say bracket negative 1, and then it can go all the way as high as it wants because it's just numbers larger than negative 1. So it go from negative 1 up to infinity. There is no upper bound. But since we can't reach infinity, you have to put a parenthesis there. And of course, you have to remember to put the bracket around the negative 1. On a number line, looks very similar. You can just bracket in negative 1 or put a solid dot on negative 1 and then shade or arrow off to the right, and you would be fine. Now, this would be a compound inequality. A compound inequality, instead of just having your x on one side and your constants on another, you've got x in the middle of this problem. No big deal. You solve for it the same way. It's just instead of having two sides of an equation where you say, I need to do the same thing to both sides, in this case, we have 3 different regions, and as long as you do the same thing to each region, you're going to be fine. So in this problem, I'm trying to solve for x. I subtract 3 everywhere to begin with. So that's what I did from here to here. In the middle, when I subtracted 3, it's just 2x. On the right-hand side, 11 minus 3 is 8. On the left, 1 minus 3 is negative 2. So now I have negative 2 is less than or equal to 2x, which is strictly less than 8. What do I do at that point? To get rid of the 2 coefficient, I'll divide by 2 in all 3 portions. Negative 2 over 2 is 1. 2x divided by 2 is x. 8 divided by 2 is 4. Now, this is a nice answer. I can say, all right, x is between negative 1 and 4. It can include negative 1, but it must exclude 4. Well, the interval notation for that is x starts at negative 1, goes up to 4, includes negative 1, so bracket, excludes 4, so parentheses. Set builder notation looks the exact same thing as the inequality notation. You just put x such that x is between negative 1 and 4. And then, for the number line, you just say, well, it has to go from negative 1 to 4. I would start at negative 1, end at 4. You either put a point or a bracket on negative 1, and then either an open circle or a parentheses on 4, whichever you prefer, and then it's just all numbers in between there. Now, for solving an absolute value inequality, what I need you to remember, and we've talked about this before, with the equations, I said if the absolute value of u is equal to some number c, that tells you that the number inside the absolute value u was either equal to c or the negative of c. Now, in inequality notation, what I'll need you to remember is if we say the absolute value of u is less than c, well, if u is a positive number, it truly does need to be less than c because the absolute value is not doing anything. However, if u is a negative number, that absolute value is actually going to be multiplying it by a negative to change its sign, which in that event flips the inequality, and that less than becomes greater than. So you just say, well, now I need the greater than sign to u. This is u is greater than the negative of c. To make a long story short, you can make these problems so easy if you'll just remember, anytime you have an absolute value isolated by itself and a number on the other side, you can say, keep the inequality, keep the other side, flip the inequality, put the greater than towards the u, and then change the sign of the other side. That process will always work in these problems. Now notice if I say, if the absolute value of u is greater than c, and I could have written this in 3 parts as well. I chose not to here, but I can say, well, that's telling me that u is greater than c. And I could also put over here, or u is less than negative c. I could have written that all in the same 3 steps, just like I did up here. So these rules are valid if the less than is replaced by the less than or equal, and the greater than is replaced by the greater than or equal. So it doesn't matter if the endpoints are included or not, you're still going to have to do the problems this way. Let's see an example of that. So if I have 18 is strictly less than the absolute value of 6 minus 3x. All right. The first step is to get the absolute value by itself. It's already done. Now, I chose to put it on the left-hand side of this inequality. That's totally up to you. You can read it on the right-hand side. That's fine. A lot of students like inequalities on the left. So I wrote it as the absolute value of 6 minus 3x is greater than 18. Please notice this and this mean the exact same thing. The greater than's to the inequality here. The greater than is to the absolute value term up here. The greater than is to the absolute value term down here. This and this exact same statement. Now, whenever I read this, I can say, well, all right, that's going to mean that what's inside is either greater than positive 18 or less than a negative 18. Those are the 2 options. Now, I wanted to go through and solve out those 2 different options here. And since there was some algebra involved, I wanted to go ahead and separate them and do them separately. First of all, I'll look at the positive case. If 6 minus 3x was already a positive number, well, that positive number had to be greater than 18 in order for that equation to be true. I could subtract 6 on each side. Negative 3x is equal to 18 minus 6, which is going to give me 12. I divide by negative 3 on each side. 12 divided by negative 3 is negative 4. Please remember, as soon as you divide by that negative, that inequality has to flip. So I'm now going to get x is strictly less than negative 4. Now, over in my other scenario where I say, well, okay, what if that inequality has to change the sign because 6 minus 3x was a negative number? Well, that means that 6 minus 3x would have to be less than the negative of 18. And here's where we work that out. You say, well, just like I did the positive version, now I need to work the negative version. I'd still subtract 6 on each side. Negative 18 minus 6 is negative 24. In my next step, I still divide by a negative 3. Negative 24 divided by negative 3 is a positive 8. Whenever we divide by that negative 3, though, that inequality had to flip from less than to greater than. And now I have x is greater than 8. Well, my solution is going to be the union of these 2. So either one of these 2 is going to be a solution set. So we say, all right, this is telling me that x could either be a number greater than 8 or a number less than negative 4. So, all right, so in set builder notation, x such that x is less than negative 4 or x is greater than 8. On a number line, it would look like this. You just say, well, we cannot include negative 4, but we can include every number to the left of it. We cannot include positive 8, but we can include every number to the right of it. The only numbers that are excluded are the values in between negative 4 and 8. And so, oh, I forgot to put the interval notation there, but the interval notation, you would say x is equal to negative infinity, parentheses, negative infinity, up to -4, parentheses, then union, parentheses, 8, comma, infinity, parentheses. That would be the gorgeous answer. I just forgot to add it in there. All right, guys, hopefully this helps out with this section. I've worked all of the homework for P9. Please look through my solutions, and that should help you out with the My Math Lab assignment. But as always, let me know if you have any questions. I'm here to help.